In this section, we're going to look at zeros of polynomials. So let's consider the factor theorem. It states for any polynomial function f of x, x minus k is a factor of the polynomial if and only if f of k equals 0. So what it's stating is that our remainder in synthetic division must equal 0 in order for us to have x minus k as a factor of the polynomial. For example, if k equals 3 is a 0 of the function, then x minus 3 is a factor. So notice that the 0 of the function is a positive 3, but when we put it in factored form, it's written as x minus 3. So our first example tells us that we are given the following k values are zeros, so we're told they're zeros of the function that we would be working with, and we want to state whether the factor would be, or state what the factor would be for the 0 given. So if we had a function and it's a 0 of the function was 7, then all they're wanting us to state here is that the factor would then be x minus 7. So it was given as a 0 is 7, but the factor is x minus 7. In our second example, we're told that k equals negative 2 is the 0 of whatever function it is that you would be working with in this problem, but our focus here is to see that if k minus 2, or k equals negative 2 is a 0, then the factor of the function would be x plus 2. So it's the opposite sign than what was given here as the 0 when we put it in factored form. And one more example is that if we were told that k equals 11 is a 0, to put it in a factored form, the factor of that function, if k equals 11 is a 0, is x minus 11. In this example, we're asked to use synthetic division in the remainder theorem to decide whether the second polynomial is a factor of the first polynomial. So if it is a factor, then we would need to do synthetic division, determine what our remainder is, and if our remainder is 0, then we can say yes, it is a factor based on the factor theorem. So doing synthetic division, we're going to use x plus 4 to decide the number that goes in the box. We're going to use the opposite sign than what it appears, so we'll take negative 4. Then we'll take the coefficients of the other polynomial, making sure we have every power represented, 4, 3, 2, 1, and none. So we can go ahead and say that we can put the coefficients as 5, 8, negative 43, 22, and 8. Our first step in synthetic division is to bring that 5 down. Then we'll multiply to get negative 20, so 5 times negative 4 gives us negative 20. Then we will add or subtract, in this case it's subtraction since our signs are different, to get negative 12. Negative 12 times negative 4, so negative 12 times negative 4 gives us 48. Since our signs are different, we'll subtract to get 5. Multiply 5 times the box, so 5 times negative 4 gives me negative 20. Subtract to get 2. Multiply times the box to get negative 8. And again, our signs are different, so we subtract and we get 0. This number right here is our remainder. If our remainder is 0, based on the factor theorem, we can state that yes, x plus 4 is a factor of the polynomial. So we'll say yes, x plus 4 is a factor. Since its remainder was 0, then it is a factor of the polynomial given. Continuing on to our next example, we're still going to use synthetic division and the remainder theorem to decide whether the second polynomial is a factor of the first. So moving down to part B of this question, we are asked, is the polynomial x plus 5 a factor of the polynomial x cubed plus 7x squared plus 7x minus 15? So again, we'll look at the second polynomial to determine the k value that goes in the box. We'll take the opposite sign than what it appears, negative 5. We'll take the coefficients of the given polynomial here. So every power is represented, 3, 2, 1, and none. So we can go ahead and do the coefficients, 1, 7, 7, negative 15. We'll bring down the first number, so bring down the 1. We'll multiply to get negative 5. Multiplying that with the box is how we got negative 5. Subtract to get 2. Multiply 2 times the box to get negative 10. Subtract to get negative 3. Multiply to get 15. And our signs are different again, so we subtract and get 0. Again, by the factor theorem, if our remainder, which is the last number here, is 0, then we have tested that yes, x plus 5 is a factor of the given polynomial. So we'll say yes, x plus 5 is a factor. Let's look at one more example using these directions. Use synthetic division and the remainder theorem to decide whether the second polynomial is a factor of the first. Again, we'll look at the second polynomial to determine k. Since it is x minus 2, we'll use the opposite sign than it appears. We'll use 2. We'll use the coefficients, so 5, 6, negative 2, 17, and 10, making sure that every power was represented first. So 4, 3, 2, 1, and 9. So we can use those coefficients, 5, 6, negative 2, 17, 10. Bring down the first number, it's a 5. Multiply 5 times 2 to get 10. Add to get 16. Multiply to get 32. Subtract to get 30. Multiply 30 times the box to get 60. Add to get 77. Multiply 77 times the box, so 77 times 2 is 154. And then add to get 164. The last number that we have here is the remainder. According to the factor theorem, in order for x minus 2 to be considered a factor of the given polynomial, we must get a remainder of 0. Since our remainder is not 0, we will say no, x minus 2 is not a factor.